All right, so let's see some linear transformations in action with Python. I'm just going to add a few little things to the toolbox this time because all we really need to do is some additional plotting things. So here's our little cheat sheet here. A lot of this we've seen before. One thing I'm doing here is adding the ability to plot a point in a particular color. So this is kind of funny, BO here. That means please plot this point in blue and make it look like an O. And then if we use R, that's for red, and there's other colors you can use as well. This one here, my gosh, this is super cumbersome. There may be an easier way to do this in Python, but I'm not that much of a Python guy, so I kind of had to futz around with this till I found it. What I want to be able to do is draw an arrowhead from one point to another, and that's so we can see the effect of a linear transformation. We want to be able to see which point it went from and which point it went to so that we can see the effect of that. And so what you're going to do is give it the from x and y coordinates, and then the two x and y coordinates, but unfortunately the way this arrow command works, you don't actually tell it the point you want it to go to. Instead, you tell it the length and direction of the line you want it to go. And so you basically have to tell it how many x units to shift over and how many y units to shift over. So I find that a little awkward, but basically we're going to solve that by just taking the 2x value and the 2y value and subtracting off the from x and y, and that's going to give it the correct length of the arrow in both directions. And then down here, it turns out it doesn't draw arrowheads by default, so you have to specify values for the head width and head length to get it to draw arrowheads. So kind of a lot of gibberish here. Don't get lost, and miss the linear algebra just for all the minutia of these Python commands here. That's just going to draw an arrowhead so that we can see the effect of linear transformation. We've seen this before. Xlim and Ylim basically just set the range of the x and y axis. This is new just because I want to be able to draw the axes explicitly. So we have this AXH line and AXV line. That stands for horizontal and vertical there. To draw the axes on there so we can see where we are and then show the plot, right? So what we're going to do in this little segment is we're going to make a function, and the function is going to be called plot transformation. And what that's going to do is it's going to plot the effect of a linear transformation, more specifically a two-dimensional linear operator. So we saw in a segment or two ago that if I have a two-dimensional matrix, a 2x2 matrix, that is essentially a linear operator that can be applied to any point to transform it into another point. And we saw that there were flips and there were rotations and there were shrinkages and expansions, and we're going to see the effect of all that. And what the function is going to do is it's going to accept as an argument a matrix that is going to be the transformation it's going to plot. And what it's going to do is generate a bunch of points randomly and plot them on the axes, and then it's going to transform each point using the linear operator that's given and plot the transform points. And the reason we need this arrowhead thing and the different colors is so that we can clearly see which point it started as and what it got translated to. Okay, so let's get started. Here's our spider thing, and of course the first thing we're going to do, as we always do, is from NumPy import splat. We're also going to do our import pylab because we need to do that if we're plotting things, right? And now let's define our function. It's going to be called plot transformation. It's going to take an argument which we'll call A. Again, the calling code can call the matrix it gives this function whatever it wants, but we, the function, are going to call whatever we've been handed A. All right, so here's what we're going to do. First, let's do the basic stuff. Let's call AXH line and AXV line so that it'll draw the axes. And we'll set up the axis limits. We'll go from -5 to 5 like I believe we did before. And then let's call pylab.show. All right, so let's just run this much here. And if I come down here, I got to make a matrix, right? So let's make a matrix. We'll call it M. And let's just start off with that being the identity matrix. So M is just 1, 0, 0, 1, and we're not even using it yet, but we will in a minute. So let's call plot transformation. Let's give it our matrix M, and we're going to get a blank plot, because that's all we do is draw the axes and set up the ranges here, right? All right, now, the meat of the function. We want to do a bunch of stuff, right? We want to do something a bunch of times, so that's just screaming out for us to use a loop. Let's do something 100 times. We're going to plot 100 random points. So we're going to use our random.rand function. If you remember, that gives us a random number between 0 and 1. So if we multiply that by 10 and subtract 5, that will give us a random number between -5 and 5. And if we do that a couple of times, we'll get two different random numbers between -5 and 5. And we'll set that equal to x val and y val, just so we sort of have a little name for those. And then let's make a NumPy vector and set it equal to x val, y val. So now we actually have a NumPy vector here. And if we want to plot it, we're going to say pylab.plot. And we're going to give it point of 0 and point of 1. Of course, we could have given it x val and y val here, but since we made the vector, let's go ahead and use it. And again, I'm going to do BO here, which plots it in a blue color, and plots it as a 0-looking thing. So let's run that and see what it looks like. And it looks like that, but it's a bunch of random points. If I do it again, I get different random points each time, right? Because it's random, duh. Now, for the meat of this thing, what we want to do is transform the point using this linear transformation matrix we've been given. And again, right here is the important part for linear algebra. We're going to make another thing here called transformed point, and all we got to do is say a dot point. That right there is the most important line on this program right here. Everything else is just minutia about how to get Python to run a loop and plot things and stuff. But this is the thing where we take a point, we multiply it by this matrix, the matrix on the left, and then we end up getting the transform point. And now all we got to do is plot the transform point. So let's do that. Let's plot transformed point 0 and transformed point 1. And let's plot it in a red color here, right? So if we run this thing, it's not going to be terribly illustrative right now because we're using the identity matrix here, right? This is the identity operator. That's what we have for M. So it basically just plotted the blues and the reds on top of each other. So let's make a different one. Let's make one called N, and we'll say that equal to an array of, how about 2, 0, 0, 2. Oops. Left out a boxing. Here you go. So N is now that guy, and we know that the effect of this linear operator is going to be to lengthen the vector, right? To take the point and to expand it in the x and y directions, make it twice as long, right? So if we run this thing with N, now our red and blue points are not on top of each other, but unfortunately you can't really see what's going on here because we haven't shown which red point goes with each blue point, right? And that's why I kind of am adding to our little toolbox here the ability to do this arrow thing. And again, it's a little clunky. We're going to have to say go from point 0, point 1 to transformed point 0, transformed point 1. Now, that's the way I think it should work, but unfortunately it doesn't. What we have to do is subtract off point 1 and point 0 because we're really not giving it the point we want it to end at, but rather the length of the line we want it to draw, right? And then, as I said before, you actually don't get any arrowheads unless you specify a width and length for the head. So let's do that. I found that this was kind of a good value, 0.2 and 0.5. All right. And then let's actually plot the other point. Oh, I'm sorry, we already did that. Right. So there we go. That's all we got to do. So let's run this thing now, and now we can see that it took every blue point and it increased it, right? Moved it twice as far from the origin because we are, multiplying both of the coordinates by 2. That's the effect of this linear operator. Now, if we made another one here, let's say we want it to go 2, 0, 0, 1. Let's say that's our N. And now let's plot it. Well, that is just going to expand it only in the X direction, not the Y, right? That's the effect of that guy. Or if we wanted to say, let's make it twice there and once there, then we're going to have it moving up, right? Or down, depending on whether it started above or below the axis, because we're just multiplying the Y coordinate by 2. Maybe we want to shrink it in one direction and expand it in the other one. So if we run that, we're going to get this kind of crazy thing, right, where you can see that every X value has been halved. We're moving it closer to the Y-axis, whereas every Y value has been doubled. It's moving further away from the X-axis, and so that's the effect of that thing there, right? So some other ones that we saw, let's do this one where it was kind of a neat flipping here, right? So what if we have -1, 0, 0, -1, and let's plot that thing. That's going to look like this, right? So what it's doing is, it's kind of hard to see. There's too many points. Let's dial this down here and make it only be like 10 points or something, right? Okay, so now if I run it, we'll be able to see a little bit better. So what it did was it took this blue point and it mapped it over here. And it took this blue point and it mapped it over here. And it took this blue point and it mapped it over here, right? So each point is going through the origin. It's basically a reflection through the origin to the opposite side. And that's because this matrix that we're doing here is multiplying both the x and y coordinates by a -1 in order to do that, right? So kind of fun. Another one we saw was a rotation. So let's do that one. Suppose I do -1, 0, and then I do 0, 1. Oh, no, I'm sorry. That's not what we want to do. We want to do 0, -1, 1, 0. Let's try that. So that's what n is now. So if we do our plot transformation this way, you can see that it has rotated it 90 degrees. It's a little hard to see because this isn't square. It kind of made it rectangular here. But it's rotating each point 90 degrees counterclockwise. And if we go back up and have a bunch of points here, you can kind of see, that it does this whirlpool effect here, where you can see that everything has been being swished around sort of circularly, right? Now, if we don't want to go quite that far, we could do this 0.7071. So remember, I said, what if it's 0.707, -0.707, and then 0.707, 0.707. Oops. Got some extra gunk going on here. Let's start that again. Let's go 0.707, -0.707, 0.707, 0.707. Something like that. Okay, so now I've got my n. And now if I plot transformation my n, now it's going to be going 45 degrees counterclockwise, right? And you remember that we said that there's a formula here. No matter what your angle that you want to rotate it at, even if it's a negative angle, you can simply make it be, cosine theta, negative sine theta, cosine theta, and it will rotate it in that angle, right? So that's just kind of a nice way to get some visualizations here so that we can see the effect of a certain linear transformation. And we will see that in our application section, where there are a lot of different things we can do once we are able to transform a vector. All right, catch you next time on All the Math.